Well, welcome everyone. This is our second KNI Distinguished Seminar of the year, I believe. And it's done in this wonderful format where you can all enjoy whatever beverage of your choice in the comfort of your living room. Before we get started, I'd just like to remind everyone to mute their mics during the webinar, please. And if you have any questions, which we very much encourage, please use the chat feature. And we will go through everyone's question at the end. We'll have time for some Q&A right after the presentation. So I'm delighted to have Peter Green join us as our KNI Distinguished Webinar today. So Peter is the Deputy Lab Director for Science and Technology and the Chief Research Officer of the NREL, the National Renewable Energy Lab in Golden, Colorado. So he actually showed me some snow. We're here in this 80-degree weather, but Peter is in the land of snow right now. So I am going to take a little bit of time to describe all the amazing accolades that Peter has accumulated through the years. So with the what's really a point of departure for Peter is that he's garnered extensive leadership experience across academia and government research settings. So you're a jack of all trades, to put colloquially. So Peter spent 11 years at Sandia National Lab and then became a professor of materials engineering, and chemical engineering at UT Austin, so University of Texas, Austin. As soon as he realized that Texas really wasn't his thing, Peter joined the University of Michigan as a chaired Vincent and Gloria Gorguzze. Is that the right way to pronounce it? Gorguzze endowed professor of engineering. As well as professor of chemical engineering, applied physics, and macromolecular science and engineering. So this sounds very much like what we do at Caltech here with many affiliations. And at that same time, Peter also served as the chair of the Department of Material Science and Engineering. And at that time, I guess this is when you started really becoming perhaps even more passionate about sustainability. And so Peter also served as the director of the Center for Solar and Thermal Energy Conversion, which is an EFRC, a Department of Energy's Energy Frontiers Research Center, and concurrently served as the president of the Materials Research Society, the MRS. And of course, those of us who are in materials, we know this is the MRS week right now. So this is a very, very active, very, very well-known society, probably the largest society, professional society in materials. Peter earned his BA and MA degrees in physics from Hunter College and his PhD in material science and engineering from Cornell University, so another snowy place. And we are delighted to welcome you here today and specifically to learn about the key scientific and technological challenges of transitioning to a future low carbon energy system. So these kinds of systems should enable carbon dioxide capture and utilization and must be able to monitor and control in real time millions of distributed energy resources in a secure, reliable, and efficient way. So we are very passionate about carbon-free future here, and especially with our focus on sustainability. So with that, I welcome you, Professor Dr. Peter Green and a friend, Peter Green, and look forward to your talk. Please take it away.
Okay, great. Well, thank you, Julia, and thank you everyone for this invitation. I'm actually delighted to be here. I was just thinking, you know, it turns out the last time I can't remember the last time I was at Caltech, but this is my third seminar. But this one is going to be very different from the prior one in that this is going to be more sort of representative of an overview. So let me upload my presentation here. Okay. Can everyone see that?
It's beautiful.
Okay, good.
No snow in this picture.
Yeah, you're right. That's right. Another time now. So yeah, the current energy system that we have right now, sort of where you have a centralized power generation using fossil energy type conventional sources, the one designed by Edison, and sort of designed for one-way distribution of power, so generates and distributes power in one direction, is becoming largely obsolete. and necessarily it has to undergo significant change. And I think it's obvious to most of us if we look at some trends happening around us. For example, if you look at power distribution from wind and solar from a distribution of sources across land and sea, EV adoption is another important one. 7.9 million EV vehicles are sort of hit the roads in 2019. And so if you think about how do you manage sort of the EV charging together with managing power use, we see it's becoming more and more of a challenge. If you ask yourself a question, pick up a city, say of 1 million people, and in the coming years, people may have an EV, they may have a range of smart devices, they have electric heaters. These are a series of, these are you counting millions of devices that potentially are connected to a grid system, operating independently, and so this is highly inefficient at one level. If you look at things at the other spectrum, you worry about the decarbonization of the industrial sector and the transportation sector because of because of the emissions. And so it's fairly clear then from these trends and these global trends that you're going to have to plan for an energy system that somehow does a number of things. One is going to help decarbonize the process, and two, to be able to manage a range of energy devices together with smart devices that people are working with. And so this change is inevitable. The energy system is going to have to be not just reliable, but cybersecurity challenges are going to have to be dealt with. And the big thing that's of interest to a lot of people is resilience. Namely, whereas with the current system, you have an event like a hurricane or something, entire grid shuts down. You're going to have to be able to develop resilient grids that ultimately don't all come apart in the midst of some kind of a disruption. And so that work's being done right now. As we go toward this future system, it's going to also have to be generate power from not just the conventional sources, but mostly renewable sources. And it's going to have to do it seamlessly. This has major economic implications. And one of the things that we worry about is that it's not going to happen because some of the decreases should happen. It's going to happen if economics really enable this to work. And what you'll see is that it's going to be successful years from now. It's a multifaceted, highly collaborative kind of a process that's going to have to happen for it to work. And in essence, it's going to be a truly grand challenge. And I'll show, and so what I'm going to do in this presentation is give you a sense of what the challenges are and a status as to where we are. What are some of the open questions? Oops. So let me give you an outline. I'm going to spend the first few minutes providing a context for you in terms of what the challenge really looks like and what's happening. And electrification is at the center of this. And this that follows by a sense of what the NREL vision plan looks like. And the vision plan really is centered around addressing this long-term energy system of the future. And this is why we're kind of the natural people to do this. We're not doing this alone, just to be clear. And then I'm going to describe more in terms of what the grid of the future looks like in more detail. And then the last part of the presentation, I'll talk about power generation. And the reason for power generation is that currently the grid uses something on the order of less than 10% wind and solar. In fact, to be more exact, the current generation capacity of wind and solar is about 1 terawatt. We're going to have to go to tens of terawatt. And so what does that mean? How do we get there? And then I'm going to sort of make a few final comments. So I'm showing you right now a graph of the global primary energy consumption as a function of time. And what's interesting about this is that, between 1990 and sort of 2015 or so, we find that the energy use increases significantly, but it increases at twice the rate of the population growth, interestingly enough. And so we see, and if you look beyond 2020, there are not range of scenarios that a range of organizations to the left shown here have been looking at, and many of which it turns out are not realistic. For example, the climate policies are simply saying what you need to be able to produce energy from, and what does it look like in the end if you want to reduce the amount of energy use. Those make range of assumptions about technology and adoptions. And on the other hand, the other extreme is that if we do absolutely nothing, business as usual, what we're going to find is that as the population grows globally by 20%, by 2040, the energy use is going to increase by about 40%. that is seriously problematic. So essentially, then the challenges of twofold. One, we want to decarbonize the economy and the energy system, and two, we need to reduce the energy intensity, this energy per capita. So there's a huge technological advances, scientific advances, working together in manufacturing. That's going to have to happen. And in the end, this future energy system, as I mentioned to you, is going to have to generate power from diverse sources, include fossil and non-fossil in interim for the next few years. And it's going to have to be secure, reliable, resilient. And yes, the economics are going to have to be right, because it's going to be a collaborative interaction between industry, academia, and government labs. And that all comes together, and it's going to be driven in part by some sensible policies and investments. And the policy part that I think is going to be the biggest challenge more than anything else. The science and technology will get right. Policy stuff, the right investments, that's been an issue for us always. So one of the good things that has happened in recent years, and if you look, for example, at solar power, the price, the cost of solar, dollars per kilowatt, has dropped by a factor of 10 over the last decade. This really has come as a result of not just the science, but the manufacturing, learning curve, some of the tax incentives. And so it's a combination of things that's responsible for that. Wind has dropped significantly in prices, in cost as well. And so if you look to the left over here, what things are very clear. Utility PV and wind are cheaper than the conventional sources, at least throughout most of the US. And that's true generally across the globe. The natural gas, on the other hand, is certainly viable and doing well. And the prices there fluctuate for that matter. But the key thing is that now the cost is down, and that's a good sign for renewable power. Globally, if you look, for example, at installed wind and solar, that I mentioned to you earlier, the price drops. So what you see is a rapid increase in capacity, same thing for wind. And so wind and solar together are about 1.2 terawatts. The big question, I'll get to this later on, is we're going to have to get to tens of terawatts ultimately if we're going to have to wean ourselves off of fossil fuels. And that itself is a multifaceted challenge. So having just identified the cost and some of the advances, there are a number of other things going on. EVs I mentioned earlier, right? 7.9 million EVs in 2019. The graph I'm showing you to the left right here, predictions by Equinor and Shell and other places as to what they believe to be the percent of EVs that people are going to purchase globally by 2040. And when I first saw this rendering of these predictions many months ago, I had a little bit of skepticism about 78%. But if you look recently, Wall Street Journal pointed out that Tesla is the 6th largest company in America. And there's a Chinese EV company that most of us never heard of called NIO, that is now the 4th largest automaker in terms of market capitalization. And so you begin to see also large corporations thinking about buying fleets of EVs. So the driving force is huge, is significant. Another trend we're looking at is just looking at connected devices on the internet, from just going from your smartphone, across the board. These things all use energy. All the energy devices we talked about earlier, these things are all there working independently. If you look at computing, data centers use a lot of power. And just the idea for scientific computing, video streaming, social media, what have you, that's gone up over 400% since 2015. And as we engage more in the use of artificial intelligence, machine learning, we're going to be using a lot more computing power. And so what we're seeing then is that these devices, connected devices, and energy consuming devices working independently consume a lot of energy, they're not efficient. So we're going to have to think about how do you integrate and manage these things. That too will contribute to significant economies of scale in terms of savings. This gets us now to the question of electrification, because electrification is ultimately essentially where you want everything to be, right? Because the EVs are incredibly efficient compared to internal combustion engine vehicles, like, by a factor of a third of order in round numbers. The commercial sector and the residential sector are fairly electrified, but there's still a lot to be done. Space heating, in terms of electric space heaters, far more efficient than the conventional ones. So there's a lot of room to be made. In terms of the industrial sector, chemicals, refining, mining. Again, going towards electrification as part of the process and getting away from coal. And of course, the transportation is where these most significant gains are supposed to be made. And so if you look to the right, what I'm showing you are estimates based on the NREL electrification future study. And you can, if you look, which is available. And it shows in terms of predictions where the largest gains could be coming from transportation. Again, this was done in 2018. I think if this analysis is done tomorrow, given some of the new trends that we're looking at with some of the new big oil companies like Nexera, I mean, some of the energy companies like Nexera. Nexera has a market capitalization comparable to Exxon. In fact, it surpassed Exxon briefly in October. You look in Spain, in Italy, in all these places, Orsted, again, another European company, they're looking at investing over a couple $100 billion in renewables, in renewable energy. These companies like Enel, Orsted, or Abirola are all vertically integrated like the oil majors. They have essentially have agreements where they're going to be supplying wind and solar energy for years to come. They control distributions and what have you. And so we're looking at a world where renewables has strong drivers to make a major contributions down the line. So I think it's essentially a foregone conclusion that we're in the midst of a changing world, we're in the midst of a transition that could be accelerating. So if I pause for a moment, I want to take a time just to kind of articulate some challenges that were not immediately obvious. In the first case, we're thinking about penetration of wind and solar into a grid, in some cases 60, 70, 80, 90%. What does that mean? The old conventional grid, again, generates power through sort of synchronous generation. And the new wind and solar, the power that connected to the grid by inverters, some power electronics, very different processes. So the idea, we can get to this later on, is figure out how to make this work in a compatible way. Right now, the utilities do it well for 10, 15, 20%. There's some other challenges later on going on. So we're gonna ask a lot more about power electric devices than we ever had before, and materials that we ever had before. This new grid system is gonna have to monitor and control millions of devices that we discussed earlier. How does it happen? For efficiencies. It's going to have to be secure, reliant, and resilient, and yes, cost effective, otherwise it won't work. The buildings of the future are going to be grid interactive. Today, they're primarily loads, but you're going to think of a building where not only provides its normal services by heating and cooling and refrigeration, but it's also going to provide services for charging of electric vehicles and a whole range of things. And so essentially what you like to do now is have this building in a way operate where it takes power from the grid, it can give it back, and do it in a way that the grid doesn't become unstable. And so that's another major area. In fact, large communities, that's the whole thought about how we're going to do that. And of course, the other aspect of this is idea of if you capture in CO2, you think about processes converting the chemicals or chemical feedstocks, fuels, and materials. That's a way of taking advantage of these things. So in a way, you're not reliant on petroleum. Other areas of grid, the grid needs various storage mechanisms of various timescales, from flywheels for seconds, batteries for hours, so seasonal storage, chemical bonds, pump hydro. So all of these things we're going to have to think about with this new future energy system. And of course, finally, you get to the circular economy. How do you minimize waste? Because one example, you take, for example, if you look at wind machines on the blades, they can't be recycled. You're looking at landfills, you're gonna put tens of millions of metric tons in them in the next few years. So, well, you gotta think about blades that you can be recycled so you don't do that with. That's just one example. We need not even talk about bottles for now. So that what I've done there is sort of painted a picture for you in terms of what the challenge looks like, and try to articulate essentially where the efforts are going right now and how we think about them. So in this next section, I'm just going to say a few words about NREL for those of you who are not familiar. And I'm doing it to provide a context for you to understand why it is we're tackling these problems. We began in 1977, that's actually the year I came to America, as a Solar Energy Research Institute. And so the works we've done in solar, I think many of you are quite very familiar with. One of the things I think if you talk to NREL researchers are, for example, the multi-junction solar cells, which are used in space, those came from NREL. If you look at wind, The designs of the latest blades for wind machines or the wind turbines came from NREL working with industry. There's a lot of work we're doing in the area of geothermal energy right now, looking at new advances, geothermal energy. One thing I want to emphasize to you is that when the lab began, it not just did basic science, but it had to prove its viability and its worth. And so it began connecting to industry from those years, because failure to find additional funding meant the lab was going to be shut down. And it was a real issue. They had layoffs one after another. And it was 1991 that George Bush, Senior Bush, made an NREL National Lab. There's a lot of work on bioenergy, vehicle technologies, hydrogen vehicles. And over to the right is work on buildings, the grid interactive buildings, advanced manufacturing. A lot of stuff happening here. To the right, the grid, and looking at the future grid security and resilience. That's another key place area that we're in, where we have large programs. We're on 3,000 people, 900 partnerships globally, from Exxon and Equinor to the city of LA. We're working with them on plans for 100% renewable energy use, to small towns in Africa and the Caribbean. That's the breadth of where we are. We publish as a lab something on the order of about 1,400 papers annually. Some of them are reports, technical reports that get downloaded. Our reports get downloaded by thousands every day. And there are about 600 archival scientific papers that were published yearly, again, all with university partners. We never tackle a problem by ourselves. It's always with partners, and more often than not, industry, because of the way DOE, where EERE organizes things. So, the big question then is, what does our 10-year vision look like? Because as a lab, we had to think really carefully about what is our value proposition in the decades to come? What difference are we going to make? And it's something we're worried about seriously over the last 4 years, given the current climate. And EERE management gave us the opportunity to simply do this as we thought about how we make this difference. This essentially captures where we're going. At the top, you see this integrated energy pathways. And integrated energy pathways gives you a sense as how do we make plans for what the grid of the future might look like? And given the kinds of work that we've done over the years, it's clear that we're thinking about this system of the future that's going to provide multiple services to customers, not just energy, but also energy for buildings, to manufacturing, to synthesis, and what have you. And to cybersecurity, a range of things. Electrons and molecules is an interesting one. It's like power to X. Basically, you're taking something cheap and of little value like CO2 or water and converting it using a range of processes to higher value items, chemicals, materials. And then the other areas of the circular economy. And remember, I pointed out that you're going to have to increase the capacity of wind and solar by at least an order of magnitude in the years to come. And so if you're going to do wind, you have to think about how do you produce wind blades in a way that they can be recyclable, so they're going to a landscape. Solar and the solar modules and a range of things that we think about this. Perovskites, how do you discard of things, how do you design things? So the bottom line is how do you design things in such a way that in the end, you don't end up in landfill, but they're further use for them by and large, something like you guys are thinking about a lot. So so these problems, a lot of places are thinking about at one level. But the value propositions that we can be a convening force in some areas that we're already ahead, then we can work collaboratively. So all right, let's begin with the first one, integrated energy pathways. So this idea is just the power generation, transmission, and distribution in the future system I mentioned earlier. And so just to kind of get us all on the same page, the current power system, Edison's power system or Edison Tesla system really is large synchronous generation from centrally where you're providing power and you're simply dispatching it in one direction only. It goes to the customer and used, and that's it. You know, you sort of balancing supply and demand, and that's it. This future system now, and we can see glimpses of what it has to look like, right? You're seeing solar arrays, or you see geothermal plants, you see electric vehicles, you see storage, you see wind farm, you see a range of things that are happening right now. And so as you get to this level, you're gonna have a lot more wind and solar. So these are variable resources. And they're also power electronics based in terms of the connections. So there's so we're looking at some things we've never done before in terms of applications of power electronics on the conditions that the current material systems don't do well. And so there's more work to be done. Lots of communications and control to understand what's going on. Optimization and control theory, lots being done. And if you look, yeah, as I mentioned, distributed energy store devices, interdependencies. You have different manufacturers producing sort of technologies that have never really worked together. I don't know how, are not really interoperable. How do you do that? And so you're looking at a highly complex system that in the end won't be managed by humans anymore. It's not possible. So we're thinking about autonomous systems. So you're thinking machine learning, artificial intelligence. That's the picture. And I'll give you a sense as to where we are soon on this matter. So here, it's sort of similar rendering where we're thinking about, I mentioned the grid interactive buildings. So these buildings are not only providing the normal services like heating and cooling and what have you, but EV charging and what have you. It's going to generate its own power. And so you're going to have to optimize this entire community by itself. Vehicles and mobility, sort of this whole notion of autonomous vehicles and controlling when they charge, when they don't charge. And this is very interesting. You're looking at weather patterns, you're looking at whether or not, or what's happening in an environment to determine whether or not you're going to charge the vehicles or not to be able to conserve energy. And then of course, the advanced wind plants, I'll talk about that soon. Big questions here to be done, new challenges. And the solar farms, very similar things. So this image that I'm showing you, this slide actually talks about a case where you have a series of energy assets and they're programmable in terms of attachments to them. And the whole idea, the algorithm development is to optimize the performance of these energy devices within a given environment. So if they're connected and you can actually do, then you can optimize them as a whole. And optimizing their performance in a given environment means that you're actually able to reduce the energy use. And so this kind of work's been done. In fact, I actually won our R&D 100 Special Recognition Award a few weeks ago. So this is one of the things that we're doing. At NREL, we're hiring a different cross-section of people. Guys doing a lot more algorithm development. We're actually writing papers in mathematics journals now that had never happened before. That just gives you a sense of how the changes are coming around. So this, getting a little closer now, a bit saying more about this autonomous grid. So the idea with this autonomous grid is that you think about a small area, and this small area has all the energy resources as well as smart devices that are all interconnected. And they can actually share energy. You might think of a small community where you have a series of homes and each home has storage, battery storage, it has rooftop solar, it's got a range of other devices, EV that are connected. And so all these homes are connected in a community. And in fact, there's a community in Colorado called Buena Vista where NREL has done that, by the way, working with the utility, Holy Cross. And so you can charge your car using PV from somebody else's home, but that community itself is set up in an autonomous way where everything is connected. And it's also connected to the grid, but if the grid goes down, this community can operate quite readily over some period of time or in the midst of a disaster. So this autonomous grid then would essentially operate in a whereby this one grid would simply optimize this energy performance, and then together they can optimize the performance of the entire system of communities. And so in theory, we can think of a large city divided by a series of cells, where each cell can operate autonomously. And in the end, the entire system does so by optimizing things. So you can imagine a case that you're doing a lot of optimization theory, then control theory to actually, and then there's data analytics and machine learning. So real time, you're monitoring the behavior of the system, and it's done in an autonomous manner. And so so we've done it with a small community with algorithm developments happening for really large communities. And the investments, if you look at, for example, has a lot of collaborators. There are about 60 staff members of NREL working in this area. Many of them are new. Over new meaning last 4 years, 5 years. And we have collaborators for Caltech, Michigan, ETH, Zurich, and other places. So this is an example of a project we're doing, and that is going to continue in the years to come. Now, this part with it, the demonstrating in a small community and then thinking about how do you happen to do this at scale where you have millions and millions of devices and what have you. We're actually started an entirely new program called Advanced Research on Integrated Energy Systems. This is called ARIES. And ARIES is basically this is sort of where we're trying to demonstrate in a very practical way, how is this going to happen? And so ARIES is kind of a research platform that really is designed to understand the operation of the future energy system. And as a reminder, this system is going to have a lot of energy assets that are going to vary in physical size, large numbers of them, and we're going to have to work with them so that they worry about interoperability of all of these systems. And so we're looking at energy storage, power electronics. So a lot of big groups in power electronics, hybrid systems, hybrid energy systems, namely, could be a combination of wind and storage, as one example, or using wind energy to produce hydrogen. These are all things that we're looking at right now. So at NREL, I want to bring two things to your attention. There is what's known as the Energy Systems Integration Facility. And ESIF, as it's often known, really is designed to examine or to evaluate new energy-related technologies, like inverters, for example. A utility develops a new inverter before they put it out there to simply wreak havoc with the customers' electricity. You can put in ARIES in this artificial environment to test it out and see how it performs and collect a lot of data on it as one example. And so it's a place where that operates with smaller devices, sort of less than in the range of 2 megawatts or so. It's connected to another campus, known as the Flatirons campus. Another campus has megawatt power wind, megawatt solar, megawatt battery storage, all these things, where we can actually put together a grid system and run a lot of experiments. We can do, for example, sort of black start experiments, so we can introduce faults in the system to understand how they respond. And this grid, entire massive grid system, so the 10, 20 megawatts is isolated from the regular grid outside of NREL through an agreement with our utility company, where all of these things can be done. And we're going to use a combination of that as well as a real of simulations to understand how do millions of devices operate. So that's essentially what integrated energy pathways looks like. The second area that I mentioned earlier is called electrons and molecules. So the idea is basically you're going to use cheap renewable power, wind and solar likely, to drive reactions. So you're going to convert CO2 or water to some higher value things like chemicals or fuels or materials. That's the whole idea. Another thing to look at is hydrogen. Electrolysis. How do you reduce the cost, the price of hydrogen to use? Of course, hydrogen has a whole range of uses, producing ammonia across the board to processing, to obviously hydrogen-powered vehicles. You guys are in Southern California, so there's a lot more hydrogen-powered vehicles in Southern California anywhere across the US, for that matter. And so with this, this whole idea then is it's not just producing hydrogen, but also producing, as I mentioned to you, other fuels and chemicals. And the idea is that we're working with a lot of companies, from Exxon to Shell to a range of others, where we're looking at certain kinds of processes. Can we scale them? And why us? Well, we've been doing this for quite some time. It's a big part of a big value proposition for the last 30 or 40 years, for that matter, in terms of scale up. Here's something we're doing recently, where idea is we're using electrolyzer for producing hydrogen, which you do, and using CO2 from a range of sources, and in a biomethanation reactor, produce synthetic CH4, right? So, and the idea then is why? Because Southern Cal Gas, by the way, you guys probably notice, is someone that we're actually working with on this. And there's a huge network out there for natural gas that's used to power all kinds of things across the entire US. So that's one way. It's also, that network can also be used to simply use hydrogen as well. There's a lot of work going on in that area. And so apart from the chemicals, there's also the storage capacity. If you look at this graph that I'm showing you, discharge time versus capacity, flywheels on a grid operates at a really, really short time, as a matter of seconds, batteries for hours. And you look over here, this sort of idea of producing a gas for seasonal storage. You often see the term power to gas or even hydrogen. This is something of interest. It's just one example, but lots of examples out there, some which I can't really talk about. With regard to transportation, this graph I think illustrates nicely a lot of things that are going on, where you certainly have the wind machines, solar, and so the idea you can actually produce energy for charging, for charging, or you can actually for electrolysis produce hydrogen, and then for use a biorefinery or a combination of hydrogen CO2 for producing chemicals, and then so obviously depending here. Chemicals for marine applications, airlines. There's a lot of work. There's a lot of excitement now about using ammonia fuel cell for powering marine purposes. Over here, electric vehicles. Hydrogen, people think are going to be line haul vehicles. That's where the application. This thing's going to be the key thing because of the power density compared to batteries. So that's sort of electrons and molecules. This next part I want to talk about really is on the circular economy. The idea then is that recycling. And I'm just going to pick a couple of examples. One is I talk about the wind blades. Next few years are going to be millions of metric tons of wind blades in landfills. And so you can't do that. These blades are made from thermosetting polymers. The idea now is to use thermoplastics, some thermoplastic composites. And if you look down here, here's an example of a 18-foot thermoplastic composite-based blade that you can simply recycle when it's no longer under use. And all the tests are showing things are really good. There's a company in Europe that's gone up to, I think, maybe 40 meters by and large. So there's a lot of possibilities here. So the weight limitations, the other thing too is that the other big thing about these wind machines is that the blades right now are huge. And if you ever saw them trying to transport a blade across a highway, you know what the problem is. And so using the new manufacturing processes that NREL developed with GE and Siemens, a number of partners, you can actually do on-site manufacturing of blades. And that's the plan to do long-term. The other area is looking at plastics waste in bottles. And the idea is this new consortium known as Bottle is sort of bio-optimized technologies to keep thermoplastics out of landfills and the environment. It's funded by DOE, led by NREL. And the mission really is to look at processes to upcycle plastics and to develop plastics that can be recyclable by design. To the right, you see examples of some of our partners. And so, obviously, as for the chemies and the chemists here, in many cases, we can figure out how to depolymerize a number of plastics. Not many, some cheaper than others. But Bottle is going to look at ways to deconstruct or depolymerize, and then try to repolymerize, maybe using bio-based monomers to enter into new materials. And so this is a real excitement right now. There are 2 EFRCs out there on it, and we're connected with them. Just 2 examples in papers in PNAS that hit the popular press is the depolymerization of polyethylene terephthalate and simply upcycling it. So there's a lot going on here. Again, this is NREL together with collaborators. Here there's the partners again, just some of the partners, there are others coming on board. So I get to the last part of the presentation, and it's a question of renewable power, right? And wind, and the new challenge is wind. You have less than a terawatt of wind. You want to get to tens of terawatts. How do you do this? How is this going to work? And the group of wind researchers from across the entire globe spent close to a week at NREL, a number of days at NREL, really asking really important questions about how do you articulate the grand challenges and how they lead towards enabling this to happen. And so they're basically divided in 3 areas, and this work's published in Science. And first is wind farms tend not to perform optimally. And one of the simplest ways to see this is that if you look at this picture over here, and you look at the wind machines, I never see windmills. Wind machines are wind turbines. That's what behind this one, for example, there's a wake. So there's a low energy wind coming here. And so that really reduces the amount of power that's produced by this guy, compared to where it could be somewhere else. The other challenge is that not all the wind machines are oriented in the same direction when the wind's passing through. They never optimally done that. And so you have to figure out a way, how do you control them autonomously? That's another area. So those are big questions. Trying to understand the wind resource are big, and the interaction are still questions people try to come to grips with. Forecasting is still challenges. If you look at offshore wind is popular because you can make these wind machines to be much bigger without issue. The wind resource is much better out at sea. The wind resource is much better when the wind machines are higher, when they're taller and there. So that's another big question in terms of doing just the mathematics and simulations and designing systems to optimize the behavior. And then of course, there's a grid integration. Those questions at large scale grid integration of wind into the grid at really, really high penetrations, that becomes some other adds new challenges. Here's a picture I liked a lot. So to the left, what you see is a series of wind machines at different heights. And what's clear is that as you increase the height of these machines, you look over here, and this region in the middle of the United States has great wind resources, and it's valuable for putting a lot of wind machines. If you make them a lot bigger, you can actually find them quite viable and working beautifully across much more of the U.S. And if you imagine going offshore, that becomes even more important. The power of the wind machine essentially sort of scales as the area of the rotor. So that's why you want to make this really big, and bigger than the Washington Monument. And yes, the wind velocity. And the wind velocity, as you know, fluctuates. But as you go higher up, it gets much better wind resources and much better wind resources at sea. So that explains the larger machines and trying to go offshore wherever that's possible. Solar, and as solar again is near and dear to many of your hearts, we're going to have to go up by a factor of 10. And I'm just showing you here, as the prices drop, what you start seeing, solar installations have gone up significantly. This is globally, and over in the US, it's gone up a lot over the years. This is just, to me, truly remarkable. This is a solar chart, and many of you have seen this. The point here is that each represents a different technology. And the fact that the charts are always pointing up means that we're continuing to improve in efficiencies, and these are good things. So there's still room there coming up. Silicon, of course, is the corners of the market. That's the primary sort of contributor, the primary technology that's out there. They're not the most efficient, as you guys know. Well, the 3-5 multi-junction solar cells tend to be far more efficient. 46% is 47.1% now is a record in the lab. And the whole idea then, we can't use these multi-junction solar cells expecting space for military applications because they're too expensive. It's really expensive to make. I don't want to go through it's a long discussion, but the bottom line is that we're working on ways using this so-called dynamic halide vapor phase epitaxy. We can actually produce these things much more cheaply and much more rapidly. We're not there yet, but if we could do that, then that offers new possibilities. The thin film solar cells, again, are great. Cadmium telluride, just one example, SIGs. Again, these are also making key contributions. So this is just the multi-junction solar cells coming 46%, but it's 47.1% in the lab right now. On the perovskites, yes, showing enormous promise because you can actually produce them like newspaper in principle. And there are lots of applications out there now that are just coming to light, looking, for example, at these multi-junction perovskites, wide bandgap perovskite, showing significant promise. The cost is quite compelling there as well. So there are lots of possibilities around getting to, with solar getting to the 10 to tens of terawatts. As I'm showing you right down here is a science paper. Again, all the best people around the world got together. Harry Atwood, and I think a number of you were part of this paper. But showing essentially, if you electrify everything, you can actually, if you're in principle able to do that, and not a very simple process, that's a way of true energy efficiencies requiring a lot less primary energy use, but showing potentially where solar could do through a range of technologies. Again, provided the economics are right, and that group seems to believe it. So I'm near the end right now, and I wanted to sort of circle back and talk about electrification. if you look within the last few days, just look at the Wall Street Journal for the companies like Ebirola, NL, Orsted, places like that, Nextera. If I did the math right, there are a couple $100 billion in investments that are going to be made in wind and solar over the next 5 to 10 years, which is incredible. And these companies I'm named off have sort of market capitalizations that look like oil companies, essentially. Again, it's the Wall Street Journal pointing this out. So that looks really good. We're going to have to do the electrification properly. We're going to have to figure out how do you optimize the performance of energy devices. And as I showed you, there's a lot of work being done, a lot of progress being made if they're connected. The other issue is most of the energy that you convert from coal and from natural gas to electrification, most of it's lost. So another advantage of going to renewables, by the way. And the efficiencies of EVs are significantly better than the internal combustion engines. And the EVs, of course, as you guys know, who own them, upkeep is a lot cheaper, fewer moving parts. And as you start looking at just the grid interactive buildings and grid interactive communities, as you're able to design these things right, where you have devices that you can control at scale, that's going to make an incredible difference as well. So in the end, my point is that this transition is an inevitable transition as we go from fossil power towards renewables. Nuclear is going to play a big role. There's a lot of work being done, for example, on small modular nuclear plants. You can also look at carbon capture, utilization, and conversion to fuels and materials and storage. So the fossil community or the natural gas community will play a role there. The new innovations in technologies have to occur to do this. I should mention, there's a lot of work at NREL on a lot of modeling, looking in terms of pathways. There are lots of very different pathways to get to a point where we get to a low carbon future. And so there's a lot of very sophisticated modeling that's being done to understand how that might work. So I think in the end, we'll do better, but if we accomplish this thing and accomplish it rapidly, it's going to depend largely on really sound policies. And two, we have to make sure the economics is right. Otherwise, our fellow citizens of the globe are just going to take the chances. And so with that, again, let me thank you for this invitation. I really appreciate this opportunity to talk with you guys. Okay.
Thank you so much, Peter. This was such an enlightening presentation, I think, for all of us. We don't usually get to hear what's happening in some real places like NREL, and so it's just very eye-opening, I think, for many of us to see the real, our technology or like our very fundamental research actually being practiced in a real place. So
yeah, thanks.
Very nice. So I'll start off. So I've received a couple of questions via chat. So I'll start off with one here, but please don't hesitate to just ask questions in real voice, in real person. One of the questions that came in was, what is the status of recycling the photovoltaic panels? Are those being recycled right now?
Yeah, so in fact here at NREL, we have an entire group that's really dedicated to that at this point. And so at least from my point of view, we're at the early stages of plans together for deciding how to recycle. It's an important question to us. It comes on our circular materials portfolio right now. And I can't say a lot more beyond that. In terms of,
I was going to say, it sounds almost like you're not quite answering.
Yeah. No, there's a lot of thought going on there right now, but not. It's the early stages. We're at the early stages.
I see that Harry
and with the perovskites, we're thinking about green.
Oh, sorry. Go ahead.
And with the perovskites, looking at green chemicals, for example, in terms of how do we process these things in a way that's sustainable long term. So it's just these are these initial plans where we are. And there's a thing called Duramat where we're actually working with industry, looking again, this has to do with modules and their performance over long periods of time. And,
so I imagine that there's probably quite a bit of proprietary information,
huh? I should say I wouldn't go so far there because that's just me not knowing a whole lot on the topic, because I only started paying attention to this thing just recently as part of our grant plan.
Harry has been very patiently raising his digital arm. digital hand. Go ahead, Harry.
Okay, yeah, thanks. Peter, yeah, very nice talk, and thank you for laying out the strategic plan for NREL. I think it's very helpful for us to be able to see what NREL is doing. And first of all, the fact that it does strategic planning, which is certainly important for everyone to do nowadays, given all the changes that you mentioned in your talk. The question I have in short is it enough? And in particular, I've concluded that it's not, and that we are going to need to work seriously on negative emissions technologies as well.
Yes, I agree with you.
And you didn't really touch on that in your talk. And I think negative emissions is going to be important for two reasons. One is that I'm less sanguine that we're going to get to zero fuel combustion by 2050. There will always be, airplanes that don't fly with lithium-ion batteries and so forth. And there's going to be things that are just going to be hard to decarbonize, or regulations won't make it go fast enough. What about negative emissions?
That we didn't spend a lot of time on, and largely because we look at our value proposition, where we think we can make a difference, and where we think we're the right people, and where we can find the right partners, and that's essentially where we sort of where we've landed. And but the negative emissions part, we thought there are other places that are much better suited for that. But it's not that we ruled it out. But if a company came to us and said, "Here's what we'd like you to do collaboratively," then it's something we could be looking at. Yeah.
Okay, thanks. Yeah, my sense is that there's not enough sort of institutional momentum behind it, and
it's a hard problem. Yeah,
so it is.
I have
but
a quick question. As an ignorant person, what is negative emissions in contrast to, say, CO2 to chemicals or CO2 to liquid fuel?
So Julie, what I was referring to was dilute capture of CO2 from the air and the water. Yeah.
And that's another level of trying to sort of implementation. How do you implement these technologies to get it done? And so whereas we didn't consider that to be one of the key directions that we're moving in. And as we did this, we worked with a lot of our partners in our planning as to what it means, what should we tackle, and what would EERE stand for, because we also have to be very consistent with EERE goals and where they're going.
Yeah, okay, good, thanks.
I'm muted. A few more questions came in. And it seems like people are really interested in recycling. Actually, it's I guess this is a topic that's near and dear to everyone's, to many of our hearts. So one of the questions is, how promising is synthetic biology and fermentation techniques for plastic recycling?
I think it's very promising. The whole bottle consortium is centered around that, led by Greg Beckham, by the way. And I hear nothing but enthusiasm from these guys. On the other side of it too, I was at a meeting in London last year with a lot of the, on this specific topic among a lot of polymer guys. And the companies were saying that on their lives, on the future of the companies, this better work. Is what it comes down to. And there are people shared a lot of really fascinating advances in terms of depolymerizing a range of plastics, including polyethylene and what have you. Cost is always a challenge down there. So I'm very optimistic about that.
Okay, that's yeah. Synthetic biology seems to be penetrating into everything.
Yeah, and that's a big part of NREL's value proposition. With a huge bioenergy institute that's almost 40 years old, looking at these kinds of questions. And this is one of the reasons I think as a lab we got into this area, because this is not known to be a polymer lab.
Well, that's what I didn't think.
Historically, it hasn't been. But no, that changed a lot. And the work also involves developing a lot of high performance computational models to understand mechanisms. And this also is in the last 4 or 5 years. A lot of machine learning algorithms, to the point where we're developing more and more, we're looking for more money to buy bigger and bigger computers. High performance computing specifically.
Yeah, that's right.
Yeah.
You got to move to Singapore for that.
So, yeah.
Okay, are you ready for more questions? These are really interesting. I know it's 5 o'clock, but would you be willing to entertain
Oh,
a couple more?
absolutely. Absolutely. I have nothing to do with this.
So I want one question that I think is very, it'd be very interesting to get your perspective on is what are the challenges in connecting the East Coast grid and the West Coast grid for harnessing the sun?
Oh,
That's
okay.
a big grid.
That's been a very political challenge. The idea of the sort of the Eastern grid and the Western grid. And there's a study, the SEAM study, looking at connecting it and what are the potential advantages of being able to do that. And the study's out wherein you can take advantage of a lot of resources that exist in some places and not others. And by doing that, you can actually minimize the amount of energy that's used and costs and what have you. And so, yeah, that study's out there looking in details, a massive simulation on our website doing that. So from a technical standpoint, it makes really good sense, but there's been a political issue around it by and large. If you Google SEAMS, I have to be careful what else I say. Just Google SEAMS, and you begin to get a sense of what's around that, and you'll come across a study. I think that's where the question's coming from.
Probably.
And I have to be careful what else I say.
Yeah, you have to be careful about everything, I guess, huh? Okay, oh my goodness, we're having a lot of new questions coming in. So I'm going to try to combine them all. So one question that came in is about long-term methane storage. Another is on material shortages. So what is NREL doing in terms of addressing, can the material storages limit the production of various technologies that you've discussed? And from, right, I'll just let you answer.
Yeah, the methane stuff, we're looking at doing a lot of work on synthetic methane. Because, you know, from the electrolysis of hydrogen with the CO2 to produce it, using sort of biological processes. And there's, of course, the network across the entire US where essentially you can store a lot of methane. Southern California has, as you know, one of my slides showed up, a huge methane storage capabilities for long periods of time. It can also work as a network for storing hydrogen. And SoCalGas is interested, and that's who funds our work. So there's a lot of really good possibilities there coming in. Material shortages, I think the question refers to sort of critical materials used in energy technologies. That's one of the key areas that we're working in, again, with partners, by and large. The batteries, it obviously you guys know even extremely well. Some of you in the audience probably know more than I do, for sure. But there's a lot of work that we're doing in terms of just from our end is looking at safety, battery safety. So we have a lot of activities towards battery safety that we're looking at from that point of view. That's really important. We're looking at new compositions for lithium-ion batteries, sodium-ion batteries. We fund a lot of work through our LDRD program. We funded a lot of work on sodium-ion batteries and next generation lithium-ion batteries as well. So a lot that's going on, collaborating, working with Argonne, and it's a combination of computational work together with experiments.
This is so interesting. You know, I could listen to you for hours, actually, especially with all these problems that we are so passionate about here at Caltech. I do, however, have to let you go since it's already after 5. I hope that everyone here joins me in thanking Professor Dr. Peter Green.
Thank you.
Joining us, and thank you for sharing with us some of the research, cutting edge research that NREL is doing, and we always welcome you back. So thank you so much.
Yes, thank you, Julia, and thank you, everyone. If you have any questions, send me an email. If you need me to connect you with people, I'm more than happy to do that. Some of you already know the guys here, but anything I can do, just let me know. All right.
Be careful with what you wish for. You might get it.
All right. Okay.
All right. Thank you so much.
Yeah.
Thank you, Peter.